Hi everyone, let's go over an example of generating a carbocation that can be resonance stabilized by a heteroatom and form a full octet contributor. So here's our context. We have this compound possessing an alkene functional group and we are going to react with methanol and catalytic acid. What's going to happen is the methanol can be protonated by the sulfuric acid. So the methanol takes a proton from sulfuric acid to become protonated methanol. And in the first reaction step, the alkene pi electron density will be shared with one of the protons from methanol, and we will electrophilically add it. We then will show that hydrogen-oxygen bond breaking. Okay, and we have a choice, right? Do we add the proton to this carbon and form the positive charge here, or is it more stable to add the proton here and have the positive charge form at that position? Now, if we wanted to classify these, this is technically a tertiary alkyl carbocation. And this carbocation is technically secondary, okay? Secondary alkyl. However, notice that it's bonded to the oxygen atom. Okay, that's really important. So at first glance, you might say, well, the tertiary here is more stable because that one's secondary and it's less substituted. And that would be a false statement, okay? Don't fall into that trap of thinking more substituted equals more stable all the time. You always have to look at what other stabilizing factors may be present. Because here the oxygen can resonate one of its lone pairs and form a pi bond to the carbon, and this causes the oxygen to take on this positive formal charge. And in this contributor here, we have a full octet structure. Every atom has an octet, and that oxygen stabilizing the positive is actually way more stable than this carbocation itself. Technically, they are one and the same in terms of the compound, right? They are contributors of a structure. But we would say overall, this is more stable to form because it is full octet resonance stabilized. And this is less stable. There is no resonance stability afforded to that carbocation. The oxygen cannot resonate and stabilize it. It is not directly bonded to the carbocation. Now, another thing that I want to stress here is that because the oxygen cannot resonate, right, this carbon is sp3 hybridized, because it cannot resonate, what's actually happening instead is it functions as an electron withdrawing atom. And so far we've talked about how donation stabilizes carbocations, but what do you think withdrawal does? Withdrawal destabilizes the carbocation. Therefore, this is not really a true tertiary stability because of the withdrawal. I would kind of consider it to be a subpar, meaning it would be higher in energy than the average tertiary carbocation because of the destabilizing withdrawal from the oxygen. However, if the oxygen is directly bonded to that carbon of positive charge, then we can have this resonance, and the oxygen in this case is electron donating, right? It resonates to stabilize this carbocation via this full octet resonance contributor, okay? So if you were given this problem, you would have to acknowledge that you're going to react in this reaction via a carbocation intermediate, and you have a choice. Do we form the carbocation here or here, okay? And notice that there should be a methyl group here. My apologies. There should be a methyl group, as there are in these structures. Sorry about that. And you would have to make that discernment of what is more stable. And remember that the more stable carbocation will form more rapidly and to a greater extent. This carbocation is preferable because of the full octet resonance structure. This resonance structure is less stable because there's not the full octet resonance, and actually the oxygen is withdrawing and thus net destabilizing to that positive charge. Okay, so if we continued this on, it would be this carbocation that would continue to react with the methanol. The methanol would then attack, and we could then detail the mechanism to get to our final product.